Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A level, Chemistry Unit 4 for October 2023. Let's begin with the first question. In question 1, which method would be most suitable to investigate the kinetics of the reactions shown? So this is an alkene reacting with hydrogen iodide to give us that. They are all gases and they have no color, so colorimetry cannot be used. There is no change in mass. We cannot use that. We also cannot use quenching because this is used in titration with acid as well as alkali, so the answer should be B. We collect the volume of gas and then see if the gas volume is changing or not. In part B, we have this equation here. It does not involve any color change, so colorimetry cannot work. There is no change in volume, so that will not work because there are no gases produced. Since gases are not coming off, there is no change in mass. But because we have an alkali, we can titrate with an acid, so the answer should be D. In question 2, the equation for the reaction of bromide 5 ions with bromide ions in acid solution is shown, which is this one here. They say the rate equation for the reaction is, this is rate is equal to K into the concentration of bromide 5 times the concentration of bromide times the concentration of hydrogen ions squared. They say the concentrations of all the reactants are doubled. By what factor does the rate of reaction increase? If we double the concentration terms, so this is going to be 2 times BrO3 minus, 2 times Br minus, and 2 times H power 2, which is going to be a 4. So a 2 times 2 times 4 gives us 16, so the rate is going to increase by a factor of 16, and this is going to be the answer. In question 3, this question is about rates of chemical reactions. Which graph shows a reaction that is zero order with respect to reactant Q? If it's zero order, then it's going to be shaped like that, so the answer is going to be A. And in part B, the equation for gas phase reaction is shown, which is this one here. The reaction is first order. When the initial pressure of A is 2 atmospheres, the half-life of the reaction is 20 seconds. What is the half-life of the reaction when the initial pressure of A is 4 atmospheres? Remember they told us this is first order, so half-life should not change. Therefore, the half-life is still going to be 20 seconds, so the answer should be B. In question 4, the graph shown can be used to obtain a value for the activation energy EA of a reaction. So this is the graph given to us, and they say the activation energy is related to the rate constant by the equation. This is the equation. They say from the graph, the EA is equal to, this graph is in the form of y is equal to m times x plus c, where m is going to be the gradient. So the gradient is equal to negative EA over r. And so EA is going to be negative gradient times r, so the answer should be C. And next they say the energy cycle for dissolving calcium chloride in water is shown. They say the enthalpy change of hydration of the calcium ions is negative 1650 kilojoules per mole. What is the enthalpy change of hydration in kilojoules per mole of the chloride ion? Enthalpy change of hydration of both is going to equal to the lattice energy plus the enthalpy of solution. So here we have the 1650, which is that, plus twice into that is equal to negative 2258 plus negative 120. And making the delta H for hydration of chloride the subject, I got negative 728 divided by 2, which is negative 364 kilojoules per mole, and the answer is going to be B. And in part B, why is the enthalpy change of hydration for magnesium ions more exothermic than calcium ions? Magnesium cation is smaller than the calcium ion, so it's going to have higher charge density, and the answer should be C. In question 6, heating copper 2 nitrate results in the equilibrium shown, which is this one here. They say what is the expression for Kp? In Kp we consider the gases, so this is going to be ignored and that. So Kp is going to equal to the partial pressure of nitrogen power 4 times the partial pressure of oxygen. So the answer is going to be D. And in question 7, when concentrated hydrochloric acid is added to methanoic acid, an acid-base reaction occurs. So this is the reaction shown. We can see this acid reacting with that to give us that. They say, what are the Bronsted Lowry acid-base conjugate pairs in this equilibrium? In the forward reaction, this is the acid because it becomes a base or it loses the hydrogen. And this is the base because it receives the hydrogen. So here the answer is going to be D. Acid 1 is HCl. Conjugate 1, meaning conjugate for acid 1, is going to be Cl minus. And acid 2 is going to be this one here, and its conjugate is going to be that. So D would be the answer. In question 8, at 100 degrees Celsius, pure water has a pH of 6, but at 25 degrees Celsius, it has a pH of 7. This is because at 100 degrees Celsius, there is more dissociation of hydrogen ions. That's why the pH is going to be lower. But at 25, there is less dissociation of water, so there are going to be fewer hydrogen ions, and therefore the pH increases. So the answer is C. The dissociation of water is endothermic, so the concentration of hydrogen ions is higher at 100 degrees than at 25 degrees. And in question 9, for beakers each containing equal volumes of 4 solutions, beaker 1 contains 0.01 mole per decimeter cubed sodium hydroxide, beaker 2 contains 0.01 mole per decimeter cubed ammonia, beaker 3 contains 0.1 mole per decimeter cubed sodium hydroxide, and beaker 4 contains 0.1 mole per decimeter cubed barium hydroxide. They say the pH of the 4 solutions was measured. Which of the following gives the order of decreasing pH? I'm going to begin with the hydroxides because they release OH minus ions, and these are responsible for a higher pH. 0.1 mole per decimeter cubed of the same volume of this, because they said equal volumes, is going to have twice the number of moles that will be present in this one, because 1 mole of barium hydroxide has twice the number of moles of hydroxide. So this has the highest pH. And then we'll go to sodium hydroxide, because this has a higher concentration in comparison to that. Then number 1 will be 3, and this is going to be the last because it's a weak base. So the order is 4, 3, 1, and then lastly 2. So the answer should be D. In question 10, this question is about the reaction scheme shown. So they say which reagent is required for reaction 1. Reaction 1 is converting a carboxylic acid to a primary alcohol. That is reduction, so we need lithium tetrahydride or aluminate 3, and the answer should be D. And then they say reaction 1 has a yield of 90%. What mass of 2-methylpropanoic acid is required to produce 6.66 grams of 2-methylpropan-1-ol? So they've given us the corresponding molecular masses. Here I began with the mass given. To calculate the actual moles, this is going to be the mass divided by the molecular mass, which is going to be that. And I got this as the number of moles, but this is for the product. So the theoretical moles using that and the yield, theoretical moles are going to be the actual divided by the yield times 100, and I got 0.1 moles. Then I use the ratio to find the moles of the acid because the ratio is 1 to 1. The moles of the acid are going to be exactly the same. Remember, the acid is a reactant. I was working backwards. And finally, the mass of the acid is going to be number of moles of the acid times MR, which is 0.1 times 88, and I got 8.8 grams, or you can say 8.80 grams. So this is my answer. Next, they say which condition is essential for reaction 2. In reaction 2, we're converting a carboxylic acid to an acyl chloride. We need PCl5, and PCl5 has to be dry. There is no water, so it should be anhydrous. In part D, reaction 3 and 4 produce the same ester, which is an advantage of using reaction 4 to produce this ester in the laboratory. So reaction 3 here will produce, an ester, and as well here. This is going to require carboxylic acid, and this is going to require an alcohol because we already have an acyl chloride here. This one does not require heating, and actually we get a higher yield in comparison to this one. This one here is going to be reversible, and there is going to be kind of a lower yield, although here will produce some toxic products. So it can be carried out at room temperature. The answer should be A. And next I say which diagram shows 2 repeat units of the polymer formed by polymerization of propane 1,3-diol and benzene 1,4-dicarboxylic acid. So this is reacting with that. This is the dicarboxylic acid and that is the diol. If a reaction occurs between the two, the alcohol is going to lose a hydrogen as this loses OH, so water is going to be produced as the two join up. And then the alcohol is going to lose a hydrogen at the end, and this is going to lose OH. So we will create something like this. But since the question is asking about 2 repeat units, so it's going to be that and then another unit, so the answer is a D. In question 12, polymer waste may be disposed of by incineration. At a plant carrying out this process with polypropylene, a waste gas was produced that was thought to be either propane or carbon dioxide. These compounds have the same molecular ion peak in a low resolution mass spectrometer, but can be separated at high resolution. So here they've given us some relative atomic masses corresponding to the different atoms. And they say which are the correct relative molecular masses. So I calculated for propane using the components here. Propane has 3 carbons and 8 hydrogens. So 12.0000 times 3 plus 1.0079 times 8 gave me that. And for carbon dioxide, 1 carbon and then the 2 oxygens giving me that. So the answer is going to be a D. In question 13, a thin layer chromatogram of a mixture of 2 compounds X and Y is shown. So they say, what is the RF value for compound X? To find the RF value, we need to measure the distance from the baseline to the compound, and then we measure the distance from the baseline to the solvent front. So we'll divide this distance by that distance in order to get the RF value. So when I did that, I got 0.38 as my answer, and that is going to be a B. And next they say Y traveled further than X. How do the attractions between Y and X to the stationary and mobile phase compare? If Y traveled further, it's not attracted to the stationary phase, it's more attracted to the mobile phase in comparison to X. So the attraction between Y and the stationary phase is going to be weaker than the attraction between X and the stationary phase. And the attraction between Y and the mobile phase is going to be stronger. That's why it was able to move further, because it's more attracted to the mobile phase in comparison to the stationary phase. So this brings us to the end of section A. Let's continue to section B. In question 14, this question is about the nucleophilic addition reaction between ethanol and hydrogen cyanide in the presence of potassium cyanide as a catalyst. The equation for the reaction is shown. They say give the IUPAC name for the organic product. The organic product is going to be this. So this has 1, 2, 3 carbons. So it's a propane nitrile, but there is OH on carbon too. So we call it 2-hydroxypropane nitrile. Next they say, complete the mechanism for this 2-step reaction, showing the structure of the intermediate and including curly arrows and relevant lone pairs and dipores. So in the first step, we will put the partial charges, partial plus, partial minus, and then the lone pair on the carbon in the CN comes and donates electrons to the partially positive carbon, and that bond is going to break, creating an oxygen with a negative charge in this intermediate piece. The lone pair of electrons on this oxygen is going to be donated to that as that bond breaks. So this hydrogen attaches here, creating OH, and this is our final product. They say justify the use of the term nucleophilic addition to describe the mechanism of this reaction. It's nucleophilic because a nucleophile attacks, so that is the mechanism. And the reaction is addition because 2 components are combined to produce 1. So I said in the first step of the mechanism, the attack to the electron deficient carbon is by CN nucleophile. Also, there are 2 reactant species that react to form 1 product, so the reaction is addition. And in part B, explain why the product of this reaction is not optically active even though it contains a chiral carbon atom. If we go back here, we can see here around the carbonyl carbon there is a planar shape. So the CN could have attacked from this side or that side, creating 2 possible enantiomers that could be equimolar to create a racemic mixture. So I said a planar shape forms around the carbonyl carbon, so the attacks by the nucleophile can occur equally from both sides of the electron deficient carbon. This forms 2 enantiomers that are equimolar, so the product lacks overall optical activity. So this brings us to the end of question 14. Let's continue to question 15. In question 15, a reaction vessel contained nitrogen monoxide and oxygen in a ratio of 2:1, that is the molar ratio. the mixture was allowed to come to equilibrium, forming nitrogen dioxide. The equation for the reaction is shown. They say the volume of the vessel was 15 decimeters cubed and the reaction was carried out at a constant temperature and at a pressure of 200,000 pascals. At equilibrium, there was a total of 0.69625 mole of gas in the reaction. This is very important, they say total. In the reaction vessel, and the mass of oxygen was 7 grams. Calculate the number of moles of each substance at equilibrium. So equilibrium moles of oxygen are going to be the mass divided by the mR. But if we look at the equation, it's O2, so 7 divided by 32 gave us that. But the mole ratio should be 2 to 1. So it means the equilibrium moles of nitrogen monoxide are going to be twice the moles of oxygen, which gave me that. So the equilibrium moles of nitrogen dioxide should equal to the total moles minus the sum of these two moles, giving me 0.69625 minus 0.65625. So my answer is 0.0400 mole. And next I say calculate the value of Kc under these conditions. Include units in your answer. Kc should equal to the concentration of the product here, which is nitrogen dioxide squared, divided by the concentration of nitrogen monoxide squared times the concentration of oxygen as represented here. But remember, they gave us the volume as 15 decimeters cubed, so since we already have the number of moles, we can divide that by the volume. So the moles of nitrogen dioxide were that, so divide by 15 and square that. When we divide by the volume, we are creating a concentration. Also, to create this concentration, the moles divide by the volume. The moles divide by the volume. In calculating everything, I got 0.57320 decimeter cube per mole. In part B, they say calculate the temperature in Kelvin of the reaction mixture at equilibrium under these conditions. Use the equation PV is equal to nRT and the data at the start of this question or the question. So from the question, pressure is 200,000 pascals, volume is 50 decimeters cubed. But when we are using this equation, volume should be in meters cubed. So I multiplied by 10 power negative 3 to convert it to meters cubed. My conversions are here. And the number of moles are 0.69625. So to make temperature the subject from that, temperature should equal to PV over nR, which is 200,000 times 15 times 10 power negative 3, divided by the number of moles and the R value. And I got 518.507, which is rounded off to 519 Kelvin as my answer. Then in part C, under a different set of conditions, the reaction was carried out to find the initial rate of reaction. So we can see some information in the table. They say the rate equation for this reaction is rate is equal to K into the concentration of nitrogen monoxide squared times the concentration of oxygen. Give a reason why colorimetry can be used to monitor the rate of the reaction. This is because in this reaction, nitrogen dioxide is going to be produced, which has some color, yet it's coming from components that are colorless like nitrogen monoxide and oxygen. Next, they say use the data from experiment 1 to find the value of the rate constant K. Include units in your answer. From the rate equation, making K the subject, K is equal to rate divided by these components. And since we know the rate, again from experiment 1, if I take you back, this is going to be the rate and the individual components. So we know the rate and we know the concentration of that, so just square and the concentration of that, which is that. Multiplying through, I got that as my answer. And this is how I got the units to be decimeter power 6 mole power negative 2 per second. Next, they say state why the reaction is unlikely to proceed in a single step. At the reactant side, there is more than 2 components. So there is a very low chance that those components will collide with the right energy and orientation to produce the product. So I said there are 3 reactant particles. There is a lower chance for them to collide successfully in a single step. And next they say a student proposed the mechanism shown for this reaction. So we see that and that. They say justify whether or not this mechanism is consistent with the overall equation for the reaction and with the rate equation. If we look at the proposed steps of the mechanism, the rate equation should only have nitrogen monoxide. Oxygen shouldn't be there because oxygen occurs after the slow step. However, if I try to write the actual equation, you can see it's 2 nitrogen monoxide plus oxygen to give us that. So basically, this is a wrong mechanism because oxygen appears in the rate equation, but here it appears in the fast step or after the slow step. So I said, when the slow and fast steps are added, the overall equation is generated. So this is consistent with the overall equation. However, based on the rate equation, oxygen should react in the slow step, so the mechanism is not consistent with the rate equation. In question 16, iron, lead, and zinc can be extracted using a blast furnace, but aluminium cannot. In the blast furnace, iron is extracted from iron-3 oxide at high temperature. Some standard enthalpy changes of formation and standard molar entropies are shown in the table. So in part A, they say the main reaction occurring in the blast furnace to form iron is shown. This reaction is feasible at all temperatures. Calculate the standard entropy change of the system for this reaction. So change in the entropy of the system should equal to the summation of the entropy of the products minus the summation of the entropy of the reactants. In this equation, these are the products and those are the reactants, and these are the entropy values we're going to use. This is iron here times 2 plus the other product is carbon dioxide. We have that, creating 695.4. And then for the reactants, we have that, which is for iron oxide, iron-3 oxide, and carbon monoxide, which are 3, so 3 times that. Combining those, we get that, and subtracting, I get positive 15.2 joule per Kelvin per mole. The next I say calculate the standard enthalpy change for this reaction. Enthalpy change for the reaction should equal to the summation of the enthalpy of the products minus the summation of the enthalpy of the reactants. Again, going back here, the products are going to be these, so using the enthalpy values. For iron, we have 0, so 2 times 0 plus 3 times negative 394. For iron oxide, negative 824 plus 3 into negative 111, giving me that. So subtracting, I got negative 25 kilojoules per mole. And next I say explain how your answers in A1 and A2 show that this reaction is feasible at all temperatures. To do this, ds total is equal to ds system plus ds surroundings, where the S surroundings is negative delta H over T. So when I substitute, it becomes that. Remember, the S system was positive and delta H is negative. So if this is positive and that is negative, it means the A surrounding is also going to be positive. So ds total will be positive at all temperatures, making the reaction feasible. And next I say the main reduction reaction of aluminium oxide in a blast furnace is shown. Calculate the temperature at which this reaction becomes feasible. I'm going to refer back to the values in the table, but this time I'm using for aluminium oxide and carbon monoxide, aluminium and carbon dioxide. So here we have the S system, which is going to be the difference in the entropy of the products and reactants. Again, the components, so this is going to be 2 times the entropy of aluminium plus 3 times the entropy of carbon dioxide minus the entropy of aluminium oxide plus 3 times the entropy of carbon monoxide, and I got positive 53.7 joule per Kelvin per mole. This should be per mole, like that. And then the enthalpy change, it's going to be that for the products minus that for the reactants. So the product we have 2 times 0 for aluminium plus 3 times carbon dioxide, which is that, minus the one for aluminium oxide is that, plus 3 into that for carbon monoxide. Combining, I got positive 827 kilojoules per mole. However, in calculation for ds total, the units have to match up. So since this is joule per Kelvin per mole, I have to convert this 2 into joule per mole. So I multiply by 1000 and the answer is 827 times 1000 joule per mole. So ds total is equal to the value we get here minus the delta H, or this value here, divided by the temperature, giving me 53.7 minus 827 times 10 power 3 divided by T. So my T is equal to that, which is that, and that was the answer. Next is to suggest why aluminium is not extracted from this oxide using the blast furnace. This is because the temperature required is quite high, so I say the temperatures required to extract aluminium can be achieved in the blast furnace. So this brings us to the end of question 16. Let's continue to question 17. In question 17, this question is about 4 isomers with a molecular formula carbon 4, hydrogen 8 or 2. So we have butanoic acid, 4-hydroxybutanol, ethyl ethanoate, and 3-hydroxybutanone. Next, they say these 4 isomers can be identified using 3 chemical tests. Each test gives a positive result for only one isomer. All 3 tests give a negative result for the 4th isomer. Deduce the 3 chemical tests required. For each test, identify the reagent, give the positive observation in each test, and identify the functional group of the isomer that gives the positive result. Here we have a carboxylic acid, so we'll use sodium carbonate, and then we're going to see some effervescence or bubbling. For this one here, we have an aldehyde functional group, so we're going to use Tollen's reagent. And the next is 3-hydroxybutanone, which can give a positive test using the iodoform test. So this one here is an ester. It will not give positive tests with all the others. So I say to test for the carboxylic group in butanoic acid, add sodium carbonate. Bubbling occurs as a gas that turns lime water milky is formed. And to test for the CHO group in 4-hydroxybutanol, add Tollen's reagent. Formation of a silver mirror confirms presence of the CHO group. And to test for the methyl ketone, which is that, in the 3-hydroxybutanone, add iodine in sodium hydroxide. A yellow precipitate accompanied by an antiseptic smell is going to be observed or is going to be formed. In part B, the 4 isomers can also be distinguished using NMR spectroscopy. State why it's not possible to distinguish any of these isomers from the number of peaks in the carbon-13 NMR. If we go back to the isomers, we can see this has 1, 2, 3, 4 carbon environments. Here we have 1, 2, 3, 4. We have 1, 2, 3, 4. So they all have 4 different carbon environments. We cannot distinguish them using the carbon-13 NMR. And next they say complete the table below to give the number of peaks in a low resolution hydrogen NMR spectrum of each isomer. This is environment 1, 2, 3, 4, so those are 4 peaks. Here we have 1, 2, 3, 4, 5, and here 1, 2, 3, here 1, 2, 3, and 4. So these are going to be for environments. Next they say one of the hydrogen 1 NMR spectra has a peak with a chemical shift greater than 10 ppm. Identify the isomer and proton environment responsible for this peak. This is going to be butanoic acid, and the environment is going to be due to the hydrogen, this hydrogen in the carboxylic group. Then they say the high resolution hydrogen 1 NMR spectrum of one of the isomers contains a multiplex of 5 peaks, which we call a quintet. Explain with reference to the structure of one of the isomers the presence of the quintet. So I drew this structure here, and we can see this is going to be the quintet because the adjacent carbons have a total of 4 hydrogens, and using the n+1 rule, it's going to be 4 + 1, creating a 5, so that is going to be split into 5 peaks. So I say the quintet is in the 4-hydroxybutanol as shown above. There are 4 hydrogens on the carbons adjacent to the labeled carbon, so using the n+1 rule, it becomes a quintet. So this brings us to the end of question 17. Let's continue to question 18. In question 18, pentanoic acid, which is that, is a carboxylic acid with Ka, which is that, in mole per decimeter cubed. They say a student was asked to titrate 25 centimeters cubed of 0.12 mole per decimeter cubed pentanoic acid solution with 0.1 mole per decimeter cubed potassium hydroxide solution. So this is the equation for the reaction, and I placed the components from the question. They say the teacher asked the student to sketch a graph showing the expected changes in pH as potassium hydroxide solution is added. The student first identified 4 key points for the sketch graph using 4 calculations and 1 chemical equation. These points are shown. So we can see these points here. They say at key point 1, before any potassium hydroxide has been added, the pH is 2.9. They say use a calculation to justify this value. Because at this point we've not added any potassium hydroxide, this is calculating the pH of the acid. Remember they gave us the concentration. If this is the equation for the dissociation of the acid, Ka is going to equal to concentration that times concentration that divided by that. But since these two concentrations are the same, Ka is equal to H plus squared divided by the concentration of the acid. So the hydrogen ion concentration is going to equal to the square root of Ka times the concentration of the acid. And the assumption is the initial concentration of the acid and the equilibrium concentration of the acid are the same. So 1.38 times 10 power negative 5, which is the Ka, times the given concentration gave us that. And the negative log of that is going to be our pH. So pH is 2.89, which is approximately 2.9 as given in the equation. And next I say the student deduced that the pH at key point 4 must be less than 13. Use a calculation to justify the student's deduction. You are not required to calculate the exact pH of the solution. So again, I place the equation. This is going to be the acid, alkali, and then the products. Initially, the volume and concentration of the acid, and then the concentration of that. But remember at key point 4, 50 centimeters cubed of potassium hydroxide is going to be added. So I began by calculating the initial moles or total moles of each that are added to the solution. So the moles of the acid will be the concentration times the volume in decimeters cubed. So I got 3 times 10 power negative 3 mole. These moles are in the 25 centimeters cubed of the acid that were placed there initially. The next are the moles in the 50 centimeters cubed of the potassium hydroxide that must have been added, which is the concentration given here times the volume in decimeters cubed, and I got those moles. Looking at the equation, the reaction should be in the ratio of 1 to 1, and therefore this is going to be in excess. So the difference between the two is going to be the number of moles of the alkali or OH minus left after the reaction. So here the moles of the excess alkali are going to be that minus that, giving us that. So the concentration of the excess alkali or concentration of OH minus after the neutralization point is going to be N divided by V, number of moles divided by volume, which is this moles, divided by the volume. Now the total volume is the 50 of potassium hydroxide and then the 25 of the acid, so we have 75 centimeters cubed, and converting that to decimeters cubed, I got that. Now this is concentration of OH in the solution. So pH is equal to 14 minus POH. I should make this a small p, giving us 14 minus the negative log of this concentration, and I got 12.4. So 12.4 is less than 13, and that should be the answer. And next I say the student deduced that the neutralization point of the graph at key point 3 would be at 30 centimeters cubed. Use a calculation to justify the student's deduction. Now the neutralization point is when potassium hydroxide and the acid have reacted in equal number of moles. It means this is the point when 3 times 10 power negative 3 moles of the potassium hydroxide have been used up. So here I said concentration of the potassium hydroxide is that, but the number of moles that are going to be required at the neutralization point are going to be that. So the volume required is going to be number of moles divided by the concentration, giving us 0.03 decimeters cubed. Multiplying by 1000, it is 30 centimeters cubed, so this is correct based on the question. And next I say that student deduced that when equal amounts of pentanoic acid and potassium hydroxide have been mixed at key point 3, the pH would be greater than 7. Justify the student's deduction. In this reaction, we are reacting a weak acid and a strong alkali. So after the reaction is done, the pH is going to be greater than 7 because there is a strong base. So I say this is a titration between a weak acid and a strong base. At the equivalence point, the pH is greater than 7. And next I say the student deduced that at key point 2, 15 centimeters cubed of potassium hydroxide would have been added and the pH would be 4.9. Justify the student's deductions using a calculation. Remember, a neutralization required 30 centimeters cubed. So if 15 centimeters cubed have been added, that is half of the neutralization. So here at this point, pH is equal to pKa, and the pH is going to be the negative log of Ka, which is the negative log of 1.38 times 10 power negative 5, giving us 4.86, which is approximately 4.9, as in the question. And in part B, the student then completed a sketch graph by linking these 4 points to show how the pH would change as potassium hydroxide was added. So we can see that point and then it changes all the way. This explains why the student drew the line so that in the section of the graph between 5 centimeters cubed to 25 centimeters cubed, the pH changes very little as the potassium hydroxide is added. No calculation is required. During the reaction in that section, there is a larger reservoir of pentanoic acid and pentanoate, so this is going to be the buffer region. On addition of OH minus ions from the potassium hydroxide, the OH will react with the H plus, keeping the pH almost constant. And in part C, the student carried out the titration using methyl orange as an indicator. The experiment did not give a satisfactory color change at the neutralization point, and the student continued adding potassium hydroxide until 50 centimeters cubed had been added. Describe the color of the solution during this titration experiment with particular reference to the key points on the sketch graph. They want us to use the data booklet. Because methyl orange was used, it's going to change color from red and then we'll see orange and yellow. So at key point 1, this is at the beginning, it will be red because it's going to be methyl orangine acid. At key point 2, it changes to orange and it will stay orange between pH 3.2 to 4.4. It will then turn yellow before key point 3 and it will remain yellow until key point 4. The student found a bottle labeled acid-base indicator solution in the Stoker board. The student, having checked with the teacher, used this as the indicator for the titration. The initial yellow solution turned green at the neutralization point of the titration. Suggest the identity of the indicator solution, including a justification for the color observed at the neutralization point. So this is going to be bromothimer blue because in the acid it's going to be yellow and in alkaline it's going to be blue. That is the range. Initially in acid is yellow and around the neutralization point there is a mixture of the yellow and blue color, and that's why it appears green. So this brings us to the end of question 18 as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.